Here's one from this causing the most difficulty in the cross product, the most recent one. Again, 2 to 95. So the wrench is 0.8 meters long, lies along the positive y-axis and grips the bolt at the origin. Okay. Always good pictures. Goal to understand the problem, not what's the formula, how do I get the answer. Always really strive to start off by stepping back, understanding the problem. Okay. So I've got this. My wrench is 0.8 meters long. So I could make a vector for my moment arm vector. We call that R. What is the moment arm vector then? It's a vector, right? So what vector would that be? You should be thinking 0.80 would be what we called R was the kind of R stands for like radius. That's the moment arm vector. Okay, and then forces applied at the end of the wrench 0, -3, -1. So what would that be like? 0, -3, -1. How about so 0, -3, -1. It's like kind of like this, right? So 0, and it's not in and out of the board. It's sorry, negative. It's not right. So 0, -3, -1. So 0, -3, -1 would be something like this. But that's just direction, right? That's just the direction of it, because the force is what is unknown. So that's the direction. So there's some scalar A, say, times that actually equals the force. The actual force is some multiple of that, right? If this is the direction of that applied force, and we don't know what the force is, then there's some scalar A times -3, -1 that's going to give me the force vector. And then once I get that force vector, I'm going to take the magnitude of it, and that's going to be the answer of this problem. Okay, so how am I going to get the amount of torque? So we just want to apply, we don't want to like reinvent the wheel and forget about, we just want to apply what we derived last time. What is the torque on the bolt? And is that, first of all, the torque on the bolt, is that a vector or a scalar?
Scalar.
It's a vector. It has magnitude and direction. And what is the torque vector? What's that? Yeah. Okay, but that would mean that we'd have to find theta. Okay, yeah, so it's a magnitude F, magnitude R sine theta. Can we do it without finding the angle? What's that? What's that? Okay, but I want to apply what we learned last time. This whole web work is about what? Cross product. Is it the magnitude of the cross product? Yeah, if I'm specifying the torque vector. Yeah, so if I said the magnitude of the torque, so actually yes, this is not equal. This is not a true statement. Why? Why is this not true? That's the magnitude of the torque, and I was after torque. So so this would be true, but to do that, I need theta, and we could figure that out. But let's apply, what is the actual torque vector? What we saw last time, it's R cross F. So what could I do? I could find the cross product using we know F is A times 0, -3, -1. R is 0.80. And I could use the algorithm to find the torque vector, the components. And then what would I do? So I can get a torque vector, say x, y, z. Or say x1, y1, z1, because they're not variables. They're going to be an actual torque vector. And then what do I need? I need that. What do I know about that torque vector? Its magnitude is 100. So then I could, once I get those components of that torque vector, I know its magnitude is 100, and then I can come back and solve for A. And then once I have that, then I want the magnitude of F, which is this whole vector with the A multiplied.
So what do you do with your resultant vector cross product?
That's the torque vector.
Oh, okay.
This is the torque vector, and what do we know about the torque vector? It's going to have A's in it, right? It's going to have A's in it. What do we know about the torque vector? But we're more interested in the magnitude of it, right? What's the magnitude of that? It's given as 100, right? It's given as 100. So based on the fact that we know that it's 100, we could solve for A. And given A, we know F, and then we can figure the magnitude of F. So I don't know, maybe this is easier. Maybe finding sine theta, setting up a triangle, and doing this to get the magnitude of torque, because we know that's equal to 100 also. So this might be a different way to do it. You would be solving for A in the magnitude of F there. I'm not sure which is easier. Any questions? Does it help? Yes, sir?
In this scenario, how would you find F?
What's that?
How would you find the F if you're so A is the cross product, right?
No, A is this scalar on the direction of F that when multiplied together gives you the F vector. This is only the direction of F. This is just the direction of the force being applied. We don't know how long that vector is or how much force there is.
So you would just find its magnitude?
What's its?
A. I'm kind of unclear on how you solve for F.
Okay, so I'm going to take the cross product of R and F. R is known. F has as 0, negative 3A, negative A. And when I take the cross product of that, I'm going to get the torque vector. It's going to have A's in it.
Oh, I see now. Okay.
It's going to have that scalar A in the torque vector. But I know that the magnitude of that is 100 given in the problem.
Then you can solve.
Solve for A, then solve for F. Is that better? Okay. All right, so 5 o'clock tonight, and then you have your written homework, which this first one should be pretty easy. I guess you did a lot of it together at the end. That's not going to be standard procedure. Standard procedure will be you working hard on it the whole class, doing as much as you can, and then just getting support, but not writing the answers on the board. So then you have a week to fine tune it and turn it in a week later. Okay? So you'll have the whole time to work on that, and then In-Young will come around and support you and help you make as much progress as you can, and then you have a week to finish it up. Okay? Other questions on that? And you'll turn that in recitation tomorrow. So in recitation, you'll have the written homework. No, maybe we won't do that. Let's see. Maybe we'll submit it online. Let me talk to In-Young. I think we'll probably submit online. Did I put a submission online for that?
No.
Yeah, that's probably what we'll do. Okay, but just watch announcements, okay? Just watch announcements. So yeah, you'll write it up. So you'll print out the sheet that I posted. You'll write it up professionally, and then you'll make a PDF and submit it on Canvas. But all that will be on Canvas. All those details will be on Canvas. Okay, ready to press forward? So we're going to talk about lines in space today. So let's just quickly talk about lines in R2. So this is blast from the past. I want to define a line, which means define all the points, right? I want an equation that generates all the points of the line. If I started with a point that I knew, what else would I need to uniquely determine a line? So given a point on the line, what else would I need to uniquely determine the line, what that line is? Okay, the direction. So what in your experience, you never really talked about direction. What did you talk about? Slope, okay? If you had some context, it would be the rate of change, right? Y with respect to x. The rate of change with y with respect to x, or the slope. So if I had this point, say P, x1, y1, and I had some slope, how much y changes with respect to x? Those two things together would uniquely determine the points that I have that form my line. Would you agree? Okay, now what about, now we got a new, and we're in R3 here, we've got 3 dimensions instead of 2. So we can talk about slope eventually, but when it comes to a line in space through that point, it's just not as simple as slope. Okay? But it would be as simple as what? So we've got the point, and we would need like the orientation of the line. So there is something that would make that very simple. So this is the point, by the way, 3, negative 3, 2. What kind of other thing would very quickly define a unique line in space that's kind of, slope is giving us orientation, right? So we want something to do with orientation of our line in space that goes through that point. What's that?
A vector.
He's saying a vector. Were you going to say that too? So would a vector then uniquely determine a direction and then uniquely determine a line? You should be thinking yes, okay? So here's this point, 3, negative 3, 2, and I'm going to choose this vector, negative 1, 2, 1. We're going to call that the direction vector of the line. So it's kind of taking the place of slope that we used before in R2 to get the orientation in R2. Now we have what's called direction vector. And this is our known point on the line. So what we're going to do first is we're going to consider for our known point. What vector is this? What do we call this? This vector is in, remember? Standard position. It's the standard position vector that ends up at our known point. So what vector is that? Is that the vector negative 1, 2, 1? No, what vector is that? 3, negative 3, 2. Right? If you take a vector and put it in standard position, meaning its tail at the origin, then its tip ends up, its coordinates are the same as the components of the vector, right? Because that's the amount of change, right? The amount of change in each direction will take you to, from the origin, will take you to the final point. So we good so far? So that's the known point, but now written as a vector in standard position. From there, I want to consider the, I'm going to take my direction vector and I'm going to put its tail at the tip of the, so that's the vector negative 1, 2, 1. And so that's the orientation of my line, right? So didn't I just find another point on the line? What point did I find? So this is a new point on the line. So I had the point, what? 3, negative 3, 2. Now I have another point. What's my new point on the line?
2, negative 1.
He wants 2, Negative 1, 3. Agree with that? How'd you get that? Yeah. That came from what? Starting at my known point and then just adding the direction vector components to generate that new point. So how can I get still a third point? What could I do to generate another point? Add it again. So he wants to put another direction vector starting there. And what's that the same as doing? Scaling this vector by how much? By 2. So now I can take that direction vector and I could scale it by 2 and add it to my known point. And what point will we get then? So here we are at 2, negative 1, 3. And it would be, what, 1, 1, 4? Is it 1, 1, 4? So how can I get, now I got 3 points. So how can I get all points on the line? What would we do to generate all points on the line? If I added any scalar multiple of the, yeah. And so how do we get the, yes, how did I, exactly. If I add any scalar multiple of that direction vector, then at the tip of the direction vector would be new points on the line, right? I would generate points on the line. So going back to this first one, how did I get the 2, negative 1, 3? I added the known point as a standard position vector, right? Plus the direction vector. And so can you imagine what the vector sum is then? What's the vector sum of those two? Are you imagining this? So this red vector is like a standard position vector that represents any point on the line. Because when I scale my direction vector and add it to the known point, I get this sum, which is the red vector. And that red vector is representing every point on the line as a vector in standard position. Do you see that? This is how we do lines in space. We take a known point as a vector. We add any and every scalar multiple of a direction vector and add those two together. And that will generate all the points in the line, which we represent by the red vector. So then that's all of them. So we had, for t equals 1, so our scalar, what we usually use for the scalar multiple of the direction vector is t. So this first one here was for t equals 1. We just simply added the added it together, right? So we added what? We added 3, negative 3, 2. Plus what? 1 times the direction vector, negative 1, 2, 1. Is that right?
Are you getting the one that's from the second vector from?
We just added one of them. That's what I'm showing right here. We just added the direction vector.
Okay.
But that's like scaling it by 1.
Oh, okay.
Yeah. So then the next one we did was we said, let's take 2 times the direction vector. So what would it be? We start with the same known point. And then we added 2 times that direction vector. And what was the result then? that equaled, so I'll do it in red. What did I get for that? That was the 114, right? What did I get for the first one? 2 negative 1, 3. And let's do one more. Let's say, let's make t negative 4. So for every value of t, every scalar multiple of my direction vector generates a particular point on the line. So when t was negative 4, I would start with my known point as the position vector. So go from the origin out to 3, negative 3, 2. And I'm going to add negative 4 times negative 1, 2, 0. And what does that get me? So 2. Yeah, this is not right here. Are all these wrong? Negative 1, 2, just the 1 here?
Yeah.
Okay. Now do I have it right? Great, thank you. And then, so when do I get what? 7? Negative 11? Negative 2? So let's see that point. Let's look at that point. So that's when I scale it by negative 4. So that's good, scaling it this way. So that's that point right there. And what's the coordinates of that point? 7, negative 11, 2. Negative 2, thanks.
So points will always be represented as a vector from standard position.
Right. So it's like we've got this vector in standard position, and it's gonna, as we get different points, it's gonna sweep out different points, right? So this is what's called the vector equation of a line. The vector equation of a line. So let's just generalize it. What did we do? We started out with a known point as a standard position vector, right? And what did we do? We added some constant multiple of the direction, and that gave us a point on the line. Isn't that what we've been doing every time? Starting off with our P naught, our known point, adding any scalar multiple of a direction, and when you add those two vectors together, you get the red vector. So let's do that. So let's write that out. Let's write out the vector components. So P naught is X naught, Y naught, Z naught, and is that fixed or varying components? Fixed or varying? Fixed, that's our known point. All right, plus T. T is fixed or varying? T varies, right? V is, we'll call it A. It's the direction vector of the line, ABC. Is it fixed or varying? Fixed. And then, when you do that addition, like we've done every time, we get point X, Y, Z. Fixed or varying? Are these components of this vector P fixed or varying? Vary, right? So so we have our known point and a direction. Those are fixed. We vary T. We scale that direction vector, and we get all the various points on the line. T and okay, so write the vector for our particular line that we did, write out the vector form of that line. So now we're going to apply that to this line that we just found. Write the vector form of our line. Who can tell me what that is? Anyone? Did you get it? So I'm gonna write out our line. A vector equation like this that generates every single point on the line. So what would that be? It's going to look just like this, but it's going to be for our line, the one that we did.
So 3, negative 3, 2.
3, negative 3, 2.
Plus t times negative 1, 2, 1.
Plus t times negative 1, 2, 1.
Does that just equal x, y, z?
He wants that to equal x, y, z. Yeah.
Can't you distribute and simplify it?
Oh, we're doing that later. We want to keep. I want to keep the vector form. Yeah.
Okay.
Yes. We can do some math on this, and we will. Not yet. So this equals what? If I let t vary, then I get all the various points, x, y, z. So I should have put the box around the other one. That's that's the yellow line here. The box goes on this. We usually put the x, y, z on the left, but doesn't matter. So this is called the vector form of the equation of a line in R3. The vector form. So tell me your name again. You're in front. Brian. Brian wants to do some math on this, right? So we can do some math, right? We know we're vector experts. So what's another way to write x, y, z? Do the math. Do the math. So x, y, z equals?
Form 3, negative 3, 2.
No, do the math, right? So multiply and add, right? Do the math. What do we get?
3 minus t.
3 minus t.
Negative 3 plus 2t.
Negative 3 plus 2t.
2 plus t.
Agree? Right? Scalar multiplication means multiply the t by all the components. Addition is like falling out of bed, right? Just add the like components. And when you do that, you get that. And now I can eliminate vectors altogether. I can say x equals what? 3 minus t. Y equals negative 3 plus 2t. Z equals 2 plus t. So this is a set of equations now. Vectors are gone. There's no vectors anymore. See that? And what kind of equations are those? You're from Calc 2. Well, yeah, they are linear. That's true. But when you have a set of equations that are generating a point in this way with a parameter t, remember what that's called?
Parametric curve.
I kind of gave it away, right? So this is a parametric. These are parametric equations, right? So this is the parametric form of a line in R3. So this was the vector form. This is the parametric form, but I meant to do this on the vector form. Not our line. Kind of messed up there. So let's yeah, that's the parametric form of our line. But what's the so looking at what we did, what's the parametric form of any line? X equals x naught plus at. Then y naught plus bt and c naught plus ct. So that's generic. That's what I meant to box and label. So this is the parametric form for our line, the one that we did. Here's the vector form of our line. What I've put boxes around are then just the general forms of those. Okay, so now I'm going to ask the question. Now we've got here's our line. X equals 3 minus both of them, right? So this is our line here. And exactly mathematically equivalent is this here. This is our line here. So the question is the point 10, negative 8, negative 1 on the line? The one that we did. Is 10, negative 8, negative 1 on the line? Figure it out. How would we figure it out? So 10, negative 8, negative 1, what are those? So those values of t, those values of x naught, y naught, z naught, are they x, y, z? What are they? Those are just x, y, z's, right? So how can I know for sure if this point, 10, negative 8, negative 1, is on our line? This one down here at the bottom or up here? Yes, sir?
Just pick any one of the x, y, z values.
Okay.
Set it equal to its respective x, y, z
Okay.
equation. Solve for t and see if that t returns the right results for the rest of the.
So you already said that was perfect, right? So we're going to say if x was 10, there is some t value that'll give us x is 10. Then the question is, does that same t value give us y and z of negative 8 and negative 1 or not, right? So 10 equals, what t value is it? That's negative 7, right? So t equals negative 7 gives us y equals negative 17. And gives us z equals right, negative 5. So now we can answer. Is that point on the line? No, because t equals negative 7, which gives us x equals 10, gives us different y and z coordinates. This point's not on the line. So the key is, how do we get points on the line? Different values of t. Scaling that direction vector in either direction, positive or negative. Each time you scale it and do that, you get a different point on your line. That's how you generate points, according to this equation. Questions on that? Okay. Erase that. All right, I'm gonna write the equation of a line. See if you notice anything here. What is this? So violet. So here's the equation of a line. So here. XYZ equals two, negative 1, 3, plus t times 2, negative 4, negative 2. So here's this equation of a line. Any observations? What's that?
The same line,
How is that possible?
because you just took the original direction vector and multiplied by 2.
Negative 2. So I scaled the direction vector by negative 2. And then what about this point? It's on our other line. So I picked a different starting point. And then for the direction vector, I did a scaled version of this one. Conclusion? What will happen?
They're parallel lines.
Parallel?
They're the same line.
Same, right? It's going to generate the same points, but for different t's, right? For a different matching of t's, right? A different mapping of t's. I'm going to get all the same points that I got on the one I did before, because my known point is on the same line, and you can have any scalar multiple of your direction vector is like the same direction vector for the line. It's the same orientation. So not only do you have an infinite number of points to choose from for a given line, but you have an infinite number of ways to express its direction. So be careful. This is an issue, right? That doesn't work in R2. The starting point can vary, but the slope or the rate of change is fixed for a given line, right? Here, the direction can be expressed as any constant multiple of a direction. Okay, but as soon as I choose a point off of the line, right, so how do we have parallel lines then? How do we have parallel lines? Right, has parallel direction vector, right? So direction vector is a scalar multiple of the other direction vector, but they go through different points. That would be parallel lines. Okay, any questions? So the sheet I gave you want to turn to the side that says, find the equation of the line at the top. Number 1, find the equation of the line.
Yeah, you're fine. You're all set. Yeah.
Do you want the vector form simplified?
No, this is vector form.
Oh, okay.
So we take the y value given to us as r to y It's the same equation that we just keep the variable. Yeah. This is cheating on ourselves here. So you set this y value equal to the y component, solve for t, and plug t into the rest of it. So y is the Yep. Yeah. Because you do it representative. Yeah, the line. Yeah, so it have like the same coefficients for the t negatives, just different x naught, y naught, z naught values. So, well, you're basically just plugging these numbers into these right here. Yeah, because these numbers, these numbers right here represent like the original XYZ coordinates of the original point. So, yeah, plus two, because it's not. Yep. Yeah, that's it.
Oh, okay, yes.
Yeah, so it's like the flat plane vertical is something like yeah. So it's the one that it isn't. Sorry, I had to visualize it to see that because it's like every point that we're x is 0. So we need to find a point where it touches.
What is smoothing again?
That's
Oh, they just never touch.
never touched, but they're not parallel.
Okay.
Okay, so we have a minute left. You can check. I wrote the answers to 1 through 3 up there if you want to check your work. There's lots of ways to do number 1, so I put 2 possibilities up there. I only wrote the parametric equations for the first. A value of t and some value of s that generate the same point. So actually, we could start with same or parallel first. If they were the same or parallel, then what would be true? Same direction, right? So we could look at those direction vectors, and if they're parallel direction vectors, then we know we either have the same or a parallel line. Is that right? So this one is what, 2, -1, 3. And this one is 4, -2, 5. So could we look at those two? Do they have to be exactly the same to be parallel? Scale multiples of one another, right? Parallel. Are they? No way. Okay? So they can't be the same line. This can't be the same line. They can't be parallel. So we got 2 more possibilities. There is an intersection point, or they're not parallel and they don't intersect. That's called skew, like this. Okay? So how do we do that? So if we assume that they're intersecting, then there's some t and some other value of s, or coincidentally the same value of s, that gives us the same xyz, right? So we assume that that's true, and then we could say the x's are the same. So we could say 3 plus 2t equals 1 plus 4s. That would be true. And then 4 minus t would have to equal 3 minus 2s. So that's 2 equations, 2 variables. And we could get the solution for t and s, and then what would have to be true?
When you plug one in instead of the other, it has to go for the same. I forgot how to solve this.
So, but in order, what's that? Yeah, then the other, so the one I've left off is the z's, right? So if I'm going to get a t and an s here, these are not, they still could be parallel lines. But if I get a t and an s for that, let's see if I do. So this is 2t minus 4s equals Negative 2, is that right? And negative t plus 2s equals negative 1. Did I do the math right?
Yeah.
And I can divide this top one by 2. See that? They're all factors of 2. So I can change that top one to t minus 2s equals negative 1. So there would be 24 ways to approach this in terms of doing these equations, okay? So you could combine any two to start, and then there's all kinds of ways to solve them. This is just one way to do it. So now I could add those equations and the t's will go away. Do you see that? I could add this one. And so what will I get? Oh, and s's go away too. Bad, right? Bad. So I get 0 equals
Oh, wow.
negative 2. What does it mean?
They don't have an intersection.
There's no way these could intersect. Because there's no t and s that even make the x and y
Yeah.
the same. Right? So it's bad. So no intersection. Skew. These are skew lines. So if I'd been able to solve these and say got t equals 1 and s equals 3, does that mean they're intersecting? I got to check z, right? I got to take my whatever I would get for t and s. Those have got to give me the same z coordinate in both. If they do, now we've got intersecting lines. If they don't, still skew. Even if this would have worked out.